Right, so where did we stop? We did this. We did this.
Yes.
We did this. Yeah, we did. We did this.
Yeah.
Did you draw this?
Yes.
No.
No, you explained it.
We explained this.
Yeah.
Yeah, so what happens is the ionizing radiation comes in. Then you have some gas like argon, I think. I can't remember, I'll have to check it. I keep forgetting what it is. I think it's argon or xenon or something. And the atoms become ionized. So you know from chemistry what that means. What does it mean to become ionized? What does it mean to ionize? Say again? But which? Which is it here? Lose an electron. So the electron leaves the atom with an ion left, and the electron hits this anode, cathode and anode. So what happens is this measures the current, and when the electron hits the anode, the current changes. So you can picture it like this. You have like time and current, and it should be constant. Okay, and then when the electron hits this, you get a little sort of change. So this is what makes the sound. This makes a click sound. So if you get lots of clicks, it means there's lots of electrons, which means there's lots of ionization, which means there's lots of radiation. So more clicks means more radiation. Yeah? This is how it's very simple. This is a very, very, very thin window. Very strong thin window. I think only really beta can get in. Maybe gamma. Mostly beta. No alpha, I don't think. Can you draw this now? Geiger-Muller counter. Yeah? The radiation hits the atom and makes an ion, and the electron is released.
What's atom?
Huh?
What's atom? Atom.
What's atom?
Which
Which atom? I'm not sure. I think argon. I don't know. I would need to check. Maybe. Could you check on your phone somewhere?
Oh, it's 20?
I don't know. Type in.
Yeah, I can type in Chinese.
What gas is in GM counter?
The access to very decent windows.
need to know about this counter for the exam?
It is organic gas.
Organic? Yeah, which one?
It's just organic.
I don't know. Maybe you shouldn't use a Chinese website.
So I use Chinese first.
Try English.
Yeah. It's 500 volt.
High voltage, like 500 volts, yeah.
Neon.
Neon.
Yeah.
What number is neon? You have it?
No, we have chemistry volt.
Ben, we think it's neon. Summer's going to check what number neon is. Neon XE?
10.
10?
Yeah.
Oh.
Yeah? Right. The activity, now remember, activity is how many atoms are lost per second. The activity is proportional to the number of atoms, and they're always decreasing. Therefore, A is always negative. Mathematically, we can say A equals minus lambda n. So, for example, suppose here you have 100, let's say n equals 100, and let's say the activity is 10 BQ. So that means in 1 second, 10 of these are gone and it becomes 90. You lose 10. Remember we talked about this, the BQ?
Mm.
Yeah. Now, if later you only have 50, then you don't have 10 anymore. The activity will not be 10. It'll be less actually. The less you have, the less activity. So in other words, you can say A is proportional to n. Whoops. To n. To, what the heck? Pen. To n. Okay. So as a formula, you can write as A equals minus lambda n. Because remember, we said A is negative, usually. Okay. And the lambda is called the decay constant. Now, what's the units? What's the units? So what's the units for, okay. So what is A? A is atoms per second. And what's the N? Number of atoms. Isotopes, rather. So they cancel. So the lambda is in per seconds. Okay, per seconds. Right, what are the units? The units are per second. Can you write that down? Activity. We did it earlier. I can show you. When we talked about BQ. Yeah? Okay.
So A is something BQ. Oh.
A is minus something BQ, yeah.
Oh.
Right. Okay? Right. What are the units of lambda? Per seconds. Yeah. Okay. In a radioactive sample, 1 mole of atoms, sorry, I shouldn't say atoms, I should say isotopes. Anyways, 1 mole of isotopes is destroyed into alpha, beta, and gamma radiation. What is the activity? Okay, so let's say we have 1 mole, and then 1 second later we have none left. What's the activity? It's minus 1 mole per second, which is minus 6.02 times 10 to the 23 isotopes per second, which we call a BQ, becquerel. So the activity is minus 6.02 times 10 to the 23 BQ. Does that make sense?
So how became they are other moles?
It decayed. So, you know, like earlier, remember we said we have C14, and C14 becomes less C14 plus N14.
Yeah.
So maybe it became something else. Maybe like it became lead or something. But you have no radioactivity left. It's picture it like this somewhere. Maybe you have like here C14, and then over time it turns into less C14 and some N14. And then at the end you have only N14.
Yeah.
So what we're looking at is we're looking at the radioactive amount. So maybe this is like 1 mole, maybe this is like 0.7 moles, and then this is 0 moles. Yeah, you get the idea? Okay, right. N is 10 to the 10. If 1,000 atoms are destroyed per second, then what is the decay constant? Okay, well, again, simple formula. You can just say A equals minus lambda N. Okay. What's the A here? What's the A, do you think? Yep. Minus 1,000. You lost 1,000. What's the N? 10, 10. So the lambda would equal 10 minus 7 per second. Yeah? Right?
7.
Yeah?
7.
Yeah. Minus 7, isn't it? Yeah? What's wrong?
Oh,
Okay. Yeah? Are you okay? Right, now. This should be good for you because you're math students too. Ben, go back to your notes. What did we say the definition of activity was?
It's the rate at which unstable nuclear decay.
Yeah. Per unit time, per second or something. Yeah. Now what I want you all to do, okay? How would we write this as a derivative? D something, D something. So look at the definition. Think about your maths lesson we had recently. What would be the derivative here? Yeah, but what letters do I put here? Huh? Mm-mm. Have a look at the definition. Yeah, so what letter?
I don't know what.
It means how many were destroyed. Yeah.
lambda.
D n d lambda? No. Let's try. So look at the definition. Activity is the is how many are destroyed per time. Okay, so now what do you think it is? Yeah, so what do I write here? What's on the top? Come on, don't be shy.
NT.
There you go, NT. A is the NDT. Okay? But remember, A is also minus lambda n. So if you put these together, you get this. Now, you remember you did this in maths class. So what you can say is that's 1 over n dn equals minus lambda dt. So what do you get here? Log n minus lambda t plus c. So that's ln, that's n equals e minus lambda t plus c, which is ec e minus lambda t. Now, if we say that when t is 0, n equals n0, that means ec equals n0. Because if you look, you get n0 equals ec e0. So
it is NO.
yeah, exactly. So you get n equals n0 e minus lambda t. But if you, okay, so that's one result. But if you remember a equals minus lambda n, then you can say a equals minus lambda n0 e minus lambda t. But this you can just call a0. So you get these two formulas, which means both graphs go down like, now I know they're really minus. I don't really care too much about the minus for these graphs. They exponentially decrease. Okay, so this is the proof of this formula and this formula. I think it'd be good to write this down. It'll be good for your maths. This proof will not be in the physics exam, but maybe it'll be in the maths exam.
Yeah. But what is A0?
What is A0?
Yeah.
The activity at the start.
At the start.
Yeah. Hmm?
Two step. Minus lambda. No.
Here?
Left.
Here?
And
Here.
Up.
Here?
The second step.
Here?
Third step.
Here?
Yeah.
You what?
Uh,
There's minus. Yeah. Do you think we'll watch this later?
maybe she finished for travel.
Maybe. She'll watch it. She flying to China?
No. Turkey.
Turkey, yeah. You got that, Ben? You cycle today?
Yeah.
It's okay to cycle.
No, drawing.
Was it? Okay. Continue? Right. So, there's a little problem. There's a little problem. Because in physics, we don't like these graphs. In physics, we like these graphs where it's linear. Yeah? So, the next question is, so I think I've got it here. Yeah. Do I? Yeah, no, actually, we'll do. I think that comes up in another lesson. Yeah, no, that's next lesson. Right, we'll do that later. So let's have a look at an example. A sample of iodine 134 has a mass of 268 grams. The molar mass is 134 grams. The initial decay activity, so that's A0. A0 is this. So let me write that down. So A0 is minus 1.32 times 10 to the 20 BQ. Okay? Right. I'll let you do just part A. How many moles of iodine are there? 2, of course. 2. 2 moles. B. How many atoms are there? 134? Oh. 12.04. Yeah? Number of iodine isotopes, yeah. How'd you get that number, Ben? What did you do? Yeah? Yeah? Avogadro, yeah? Yeah?
Is n times n just 2.
Yeah. N equals Na times N.
N equals n.
Huh?
N equals n.
Yeah?
Yeah, I
Yeah.
mean it's 3 n.
Whatever way you like it. 6.02 times 10 to the 23 times 2. It's okay, Summer? This is chemistry. Chemistry.
Yeah.
Basic chemistry. Okay. What is the decay constant?
A?
Yeah. No, lambda.
Oh,
Lambda. So you can say A equals minus lambda n. Or you could also say A0 equals minus lambda n0. Because these keep changing. So lambda would equal minus A0 over N0, which would be 1.32 times 10 to the 20 over 12.04 times 10 to the 23. Thank you, Ben. What's wrong, Summer? It's okay?
Yeah.
Okay.
it's 23. So I think
0.001.
0.001.
Like this? Okay, D. How many atoms of iodine are remaining in the sample after 1 hour? So that's this formula. N equals N0 E minus lambda T. So that is 12.04, yeah, times 10 to the 23 times E minus 0.00011 times 3,600.
minus 8.1 10 23.
8.1. Yeah?
Yeah.
A. Yes.
Okay, E. What is the activity after 1 hour? Okay. A equals minus lambda n, so that's minus.
No, it's A equals AOE minus lambda.
Yeah, you can use both formulas, you get the same answer.
But how?
Okay, we'll do it both ways, Ben. So you could say A equals minus lambda n, or you could say A equals A0, E minus lambda n, lambda t. So this one here would be minus 0.00011 times 8.1 times 10 to the 23. And this one here would be minus 1.32 times 10 to the 20 times E minus 0.00011 times 3600. Okay, Summer, why don't you calculate the right, and Ben, you can calculate the left.
Minus 8.88 times 19.
Ben, what did you get?
Something difference is minus 8.91.
Ah, close enough.
Times 10 to the 19.
Yeah, that's fine. That's fine. Okay, F. How long until you have only 100 grams? So, you can also say M equals M0 E minus lambda T. So this is 100 grams, this is 268 grams, E minus 0.00011 T. Okay,
Ooh, so we use log? No.
yeah,
Okay.
yeah. Go get me the T. Go on, calculate T.
Why you add all
I don't want to use grams, I want to use kilograms. Same thing.
oh is kilogram?
Yeah, really should try to use them.
It means the right side equals.
Huh?
What is the right side?
What is the right side?
I don't know. Is at the log?
Ah, you know what to do, Ben. So what you should do first is divide. Then add log.
Yeah.
Oh, yeah. And so our right side is
Yes. Maybe this.
Okay, what did you get, Summer?
Insolence minus 61 points.
It's okay about the point. How many minutes is that?
149 minutes.
Right? right? So it's roughly 2.5 hours. G. Okay. How long until you have 1/4 of the activity? Okay. Sorry, can you still see? Getting quite small. Right. So lastly, we want 1/4 of the activity. I know what I'll do actually. I'll write it up. I'll write it up here. G. So activity equals A0 E minus lambda t. But we want 1/4 of the activity. So that becomes A0 over 4 equals A0 E minus lambda t. Yeah? Cancel, cancel. 0.25 equals E minus 0.00011 t. Log, cancel. So the t will be log 0.25, yeah, over. Say again? 12,000.
Yeah. 602.
How many hours is that? Divide 3,600.
3.5.
Ah, nice. So yeah, 3.5 hours.
Yes.
Yeah. Okay. Right. This is a good exam type of question, like section B. You know. Yeah, I think you should write it down. Yeah. Can you see it okay?
The questions.
Question.
Yeah.
Yeah, want to see the answers?
No. Maybe.
In a minute. You think so? A little bit. Maybe. A little bit. Okay, now the answers. You have it all, Ben? Somewhere?
Yeah.
Which one? You have it all?
Yeah.
Okay, great. Let's continue. Okay. Oh, good. That was the last example. Right, now, so what you have two worksheets you can do now. Decay equation and half-life. You should. I don't know what you want to do first, half-life or decay equation. Doesn't matter. Maybe decay equation and then half-life. What time is it? Ah, yeah. Okay. Okay. I'll give you time. We can do these now. Should be no problem, right? Right? No problem? Let me think. I'll tell you what. Hang on. Let me just stop this here.